So continuing on with our discussion of matter, now let's talk about elements and compounds. And really, before we can even start talking about elements and compounds, we have to consider what matter is even made of, which is atoms. So the first thing you need to know about elements is that elements are substances that can't be separated into simpler substances. Both compounds, which is still a pure substance, and mixtures can be. This means that they can't be made simpler by either a physical process, and by this I mean a separation technique. We'll talk about that at the end of the unit when we start talking about mixtures, or a chemical process, i.e. a chemical reaction. That means that they're made of one basic subunit. And what is that subunit? Well, we remember from Science 10, that's an atom. So the atom is the basic unit of all matter. Ultimately, all classes of matter can be identified or classified based on the types of atoms or combination atoms that they contain. The atom is the smallest indivisible part of matter that retains its chemical composition. It's not to say that it's the smallest component of matter, because we know, as we'll talk about in a second, that it's made of subatomic particles. But if you break it down or look at it at a level any smaller than the atom, it won't have the same chemical properties of the matter that you were talking of. So what actually makes up an atom? Well, atoms are made of three kinds of subatomic particle. When I say sub, any sub means below, so it's below the level of an atom, anything smaller than the atom. We know that there's protons. Protons are positively charged particles, and they're located in the nucleus, in this very dense center of the nucleus. Neutrons having a neutral charge, and again being found in the nucleus. They're the ones that are easiest to remember because everything about it is new. And electrons, a negatively charged particle which is outside of the nucleus. I know last year you were told that it was in either a shell or an orbit. The protons and neutrons are found in the nucleus, and they have approximately the same size. In fact, they're almost 2,000 times as large as an electron. And that has a very important impact on the structure, as we'll talk about in a second. So when we talk about the atom, we will refer to it and classify them using a couple of numbers, the atomic number and the atomic mass. The atomic number tells you the number of protons and electrons in a neutral atom. I would rather you think about it as being always the number of protons, because the protons define the element. So since the atom is neutral, we know that the number of protons must equal the number of electrons. So if you are told that it's an atom, that means it must be neutral. And if it must be neutral, then the protons and electrons must be equal. So if, for example, we're looking at mercury, it has an atomic number of 80 and therefore has 80 protons. By definition of it being an atom, a neutral overall molecule, it must therefore also have 80 electrons. So the atom also contains, as we've already talked about, this neutral subatomic particle, the neutron, and it's again in the nucleus. And as we've also already said, most of the mass of the element must come from the protons and neutrons, because they're 2,000 times as heavy as the electrons. So, because the mass of an atom is made of the mass mostly of the protons and neutrons, we say that the mass number, or the atomic mass, is equal to the number of protons or neutrons. Because of this, chemists use the symbol to show both the atomic mass and the atomic number for an atom, where the bottom number always is your atomic number. So we know for mercury that number is 80. The atomic mass is always written at the top in front as a superscript, so for mercury it must be 200. Once you know the atomic number and the mass, then you can find all three identifying subatomic particles. Now, we've only referred to so far neutral atoms, so where the protons and electrons had to be equal. But what you might remember from Science 10 is that electrons can actually be transferred. And in so doing, we can form ions. So ions are formed when atoms gain or lose electrons only. Because they're outside of the nucleus and they're not as tightly held, they can be lost. That can happen during a chemical reaction, when we heat to a very, very high temperature, when we're exposing to a very high voltage, which in physics actually refers to an electrical potential, the potential to cause an electron to move, and when ionic compounds are put into water, which is why water is such an excellent conductor. Now, metals tend to lose electrons, while nonmetals tend to gain electrons. Because of this, metals form positive ions. They end up with less negative electrons than positive protons, and so the remaining charge is positive. Nonmetals have an excess of electrons. They gain negative electrons, so they have more negative electrons than positive protons, and so they end up with an overall negative charge. So when we write ions formulas, we do so by writing the element symbol with the charge as a superscript behind. For example, Mg2+, as you're shown here, has the magnesium symbol to show that it's magnesium, and the 2+ to indicate the charge. Now when ions form, remember that only the electrons are affected, so the number of protons and neutrons stay the same. They're trapped in this very dense, highly stable nucleus. So to find the charge on an ion, all we have to know is the difference between the number of protons and the number of electrons. Magnesium has, as a neutral atom, 12 protons and 12 electrons, but when it forms an ion, it loses 2 of those negative electrons, so it only has 10. Because of this, it has a charge of positive 2. And to write its complete ionic symbol, which has all the pieces of information that anyone would need. Now the last thing we have to talk about with regard to the atomic structure on its own is what an isotope is. And isotopes of atoms are iso, meaning the same, and tope, meaning type. So the same type of atom, of the same element, but they're differing only by their mass number. Because it's for an atom, their protons and electrons are the same. So the only thing that can differ about them is the neutrons, therefore the mass. Most of the naturally occurring elements have at least one isotope, and in fact lots of them have more than one. That's why when you look at the periodic table, they don't have nice round whole numbers for their mass numbers. When we look at hydrogen, hydrogen actually has 3 isotopes. Hydrogen 1, the 1 behind it meaning its mass number. Hydrogen 2, again the 2 representing its mass number, and it has a more common name of deuterium. And hydrogen 3, having a mass number of 3, but again having a common name of tritium. Now notice when we look at the masses of the elements on the periodic table, they're not nice round whole numbers, and that's because the masses actually take into account the masses of their isotope and their natural or fractional abundances. You can look up a definition of that on page 110 of your very heavy Prentice Hall textbook. To find the atomic mass of an element, we multiply each isotope's fractional abundance by its mass and then add those products together. So when you multiply it by the percentage as a decimal, that means the part of the mass that comes from that particular isotope. So at the end, when we add them all together, that represents the total mass of all of the isotopes. So chlorine, for example, has 2 isotopes, chlorine 35 and chlorine 37. Chlorine 35 represents 75.53% of all chlorine, where chlorine 37 represents 24.47%, i.e. the remaining portion of chlorine. So to calculate their atomic mass, I take the mass number, in this case for chlorine 35, 34.969 if you know the exact number. If you don't know its exact atomic mass, you would simply use the 35 or the 37. And then I multiply that by the percentage turned into a decimal. Remember that all percentages have been multiplied by 100, so to convert between the whole number percentage and the decimal, we just divide by 100. So this first half, 34.969 times 0.7553, represents the part of the mass of all the chlorine which comes from chlorine 35. Similarly, the 36.96 times 24 and that should be 47, represents the part of the mass that comes from chlorine 37. To get the total mass, we simply add those together. And by convention, scientists have all agreed to keep 2 decimal places. That's going to be a very basic introduction, but we're going to practice the skills and review the skills that we've just introduced more in class.